Hello, everyone. So thank you to be here today. So it is my great pleasure to welcome us. Kind of a last-minute colloquium, but luckily Steve was ready to step in and fill in the spot. So this is my great pleasure to present you Steve Vance. So Steve actually got his PhD here at ESS. I'm not going to say how many years ago. I'll be polite. But yeah, so Steve started, had his undergraduate at UC Santa Cruz, then moved here, did his PhD with Mike Brown, and then pretty much got to JPL right away through a NASA postdoctoral program, and since then have stayed there, because apparently it's a nice place to do planetary science.
On a good day.
On a good day. So Steve has been involved with the Europa Clipper mission for a very long time. He was actually part of the Jupiter joint Jupiter definition, that's science definition team. So that's the first group of people that actually start to think about defining what would become eventually Europa Clipper. So he's going to talk to us about the mission and how the work we've been doing, part of it together, fits into the exploration of Europa. So we can
All right, yeah. Great. Well, yeah, thanks, Baptiste, for the introduction and the somewhat last-minute invitation. It's a pleasure to, give the departmental seminar that I was required to attend in graduate school. I hope I can keep you awake despite the lights just turning off. I can confess that when I came to the seminar, that was not always the case. I'll have lots of fun NASA-y slides. So Baptiste mentioned that I got involved in the study of what became Europa Clipper back in 2007 when I started my postdoc. That went on for longer than we would have liked. It went on for about 7 years before the mission became Europa Clipper. And there's a long story about 3 additional science definition team studies that happened. I learned a whole lot about how the federal government works and sometimes does not work. So that's a separate conversation, though. I'm happy to be here today to talk about NASA's Europa Clipper mission that has launched as of last October. So I'll also talk about the work that I'm doing with Baptiste and others. The main things are, Europa Clipper is an integrated investigation, lots of different measurements, all working together to reveal the habitability of this moon of Jupiter that has an ocean under its surface. And we now understand it's one of many oceans. And so this mission is emblematic of what I see as the future of outer solar system exploration. And so to make the return from that mission as good as possible, Baptiste and I and others have multiple projects looking at the properties of materials and how those are integrated to be able to answer some difficult geophysical questions that are ultimately intrinsic to understanding habitability. I guess if you are in Josh's class, a lot of this talk should be familiar to you because a lot of the slides here are meant to follow the structure of a paper that I led in my role as co-chair for Europa Clipper's Habitability Assessment Board, the HAB. And so I'll get into the structure of the mission, the science team, and how the HAB fits in. But suffice to say, our goal along the entire development of the mission since 2015 has been to oversee the integration of all the measurements, again, to investigate Europa Clipper. And if you don't have this paper, feel free to email me and I can send it to you. But let me just talk a little bit about Europa and the other moons of Jupiter in a more general sense. So if you were at my talk yesterday, you probably would have seen this slide, I think. Maybe not, actually, I don't remember. So this is kind of a fun thing to think about that, here's what we learned 400 years ago when Galileo looked at Jupiter through a telescope. And at that point, we didn't know that Jupiter was a planet orbiting the sun. And fast forward 400 years after the Galileo spacecraft, and here's how those little dots looked. And the 3 outermost ones we now know to be covered in water ice and some other stuff. And the innermost one is not, because it's instead covered, pockmarked with what are not craters, but instead are calderas. So Io is more volcanically active than Earth. And if only a tenth of the heat that's going into Io is going into Europa, Europa likely has a vigorous, deep liquid water ocean. And so we want to understand more about that. We can think of Europa in comparison to other promising worlds like Mars, where there's an ongoing effort to understand the context of Mars' early history when it might have been very Earth-like. And so that's right now a study to understand whether Mars had life long ago. And so that's analogous to the study of Earth's early history and the earliest rocks that show microscopic molecular signs of early life. And there's almost no water on the surface of Europa, or of Mars, rather. In contrast, there's twice as much water inside of Europa's ocean beneath its surface as in all of Earth's oceans. And so we want to understand whether Europa has the ingredients for life. And this is getting into some of the language with which we speak carefully about the mission and its goals. We want to know if Europa has the nature of water in Europa, confirm the presence of that water, understand the presence of elements that are essential to building life, so carbon, hydrogen, oxygen, nitrogen. What are the proportions of those? Where are they mixed up? And does the configuration of elements and molecules in the interior of Europa seem to be amenable to supporting life? And lastly, are those conditions such that they might have been happening for a long period of time? We know that life on Earth had a very long history that changed through time. And interestingly for Earth, as I'm sure many of you know better than I do, Earth's history is intimately coupled with the development of life. They evolved together. And we can ask whether Europa similarly has evolved through time, whether life might have been so abundant that it changed the chemistry of Europa's ocean and helped determine the fate of Europa's chemical evolution. That's a more distant goal, perhaps not one that Europa Clipper will address, but it will certainly lay the groundwork for that. So to understand Europa, we need to understand the workings of its ice shell, which shows complex geology akin to tectonic activity on Earth, both on its surface and in terms of geodynamics in the interior. We want to understand both how the ice changes with depth, not least how thick the ice is, and the properties and existence of an ocean below. The composition of the surface correlated with the surface geology, including the time scale of emplacement of material from underneath, and puzzling out what materials on the surface came from the interior versus things that came from space instead. So that's a really difficult process, or a difficult part of the mission that involves a lot of planetary geologists. I feel like the mission is motivated largely by planetary geology, and that's perhaps appropriate because Europa is a very complex place, and the place where we have the most information is its surface. So we also want to think about the future and do reconnaissance, look at Europa at the closest scales. I find this image compelling. This is showing these linear fractures that span the entirety of Europa's surface. And at detail, you can see, for one, where they're bisected and cut off, and also where there seems to be some kind of non-icy lag deposit at the base of the fracture. So indicative of both intriguing geological activity, perhaps opening and closing of the ice due to tidal fracturing, but also perhaps organic materials developing at the surface, either coming entirely from the interior or created from radioactive radiolysis, charged particles bombarding the surface, captured by Jupiter's intense magnetic field. So lots of different things for us to study. Europa is a very complex system. It's possible when we go there, we will find current activity, that is opening of these cracks, as we did at Saturn's moon Enceladus, leading to spewing of materials in space. This is, I believe, simulated activity based on what Europa Clipper might see, but it mimics putative observations from the Hubble Space Telescope conducted in 2014, which in some sense were the reason NASA greenlit the mission, because we had this compelling evidence that Europa Clipper might at least have been active at that time. Since then, subsequent studies have not seen repeat of that activity. So if there are plumes spewing things into space from Europa, they are not continuous in the way Saturn's moon Enceladus spews material into space and creates the E-ring of Saturn. So one of Saturn's rings is entirely sustained by water spewing into space. So to study all of these things, we spent a very long time studying mission architecture, but got underway putting together the details of that mission architecture in 2015 which led to the creation of the Europa Clipper spacecraft. So it's a solar-powered mission, which has a suite of instruments, only two of which are really shown here, maybe three if you count we have a radar antenna attached directly to the solar panels, which turned out to be a very complicated engineering task because basically the solar panels are now part of the radio antenna, and so generating the radio waves and also taking part in receiving them. This magnetometer boom for our magnetometry. And what else do I want to say about this slide? I wanted to point to the radar, and there are multiple radar antennas, radio antennas that are involved in the gravity investigation, which I'll talk a little bit about later. So this mission jumped to where we are today. This mission launched in October. Baptiste and Ula were out there. A few other people in this room were out there. We will arrive at Jupiter in 2030 and begin our tour of Jupiter to explore Europa, focused on Europa, unfortunately only on Europa and not the other moons for now. So we'll have a flyby of Mars in February and come back by Earth in December of 2026. So stay tuned in February for that flyby of Mars. If time permits, I can share a little bit more about that at the end of the talk. And so that'll be a chance to test some of the instruments and to get some first light ideas of how the data at Europa will look. So a little bit about the architecture of the moon. You might ask, why are we not orbiting Europa? If Galileo already flew by Europa a few times while orbiting Jupiter, why are we doing that again? Well, the reason is that we want to protect...
As I mentioned, the radiation dosage is...
Oh, that's fun. That's my colleague Sam L. So we want to keep Europa out of the intense radiation environment of Jupiter. Again, that's created by the intense magnetic field of Jupiter that captures solar wind particles and ionized particles from Io's volcanism. And so this is showing the entirety of the tour of the mission and the accumulation of radiation by the spacecraft. And so you can see this is a very sped up time scale. You can see Jupiter's moons zooming around, and the Europa Clipper on its elliptical orbit, encountering Europa at different parts of its orbit, and thereby sampling different parts of the tidal cycle of Europa, the flexing of Europa during its eccentric orbit. And the colors are indicating the accumulated dose of radiation measured in rad. And so the goal is to have 3 megarad or less at the end of the mission. So the mission design allows us to do most of the science that we would do while orbiting Jupiter by flying by Europa very close in multiple places. The closest Galileo flybys of Europa were around, I think at most 300 kilometers, but more typically more than 1,000 kilometers from the surface. The red in the lines here indicate flybys as close as 25 kilometers. And perhaps later on in the mission, as we're more confident about our understanding of the gravity field of Europa, we could get even closer. So that's really great for geophysical investigations that are measuring signals that get stronger the closer you get to the surface. It's not that great for imaging or radar, where you actually don't want your data to smear due to being too close or too fast as you're flying by. So it's a trade-off for the different measurements. But as a result of this investigation, we will develop an unprecedented global map of Europa at high resolution, in some places down to 0.5 meter per pixel, but generally on scales of 100 meter per pixel in the visual or better. And also mapping at other wavelengths, and again, mapping through the surface. And again, the reason we need to do this, and this is a figure from that paper that I mentioned, is because we want to understand all of the complex things happening in Europa. But in the interest of habitability, we absolutely have to correlate those things with what might be happening in the ocean, not least how thick the ocean is, but hopefully also clues to how overturning circulation happens in Europa. Is the ocean stratified, for example, and can we find clues to the thermal state of the interior? If Europa is tidally flexed like Io, might it have volcanism? That is, does some of that tidal heating happen in the interior, as somewhat depicted here? And if there is volcanism, is it distributed uniformly? Is it maybe at the poles? Is there topography at the seafloor? these are really interesting questions that we can begin to think about and have some confidence that we can constrain using the measurements of Europa Clipper. But maybe I should back up. I will back up because that's the topic of this talk, and explain or elaborate on this concept of habitability, because it's now intrinsic to NASA's planetary science program. It's everywhere in the decadal survey that is the guide document for NASA's science. So the paper is structured in this manner, with a section focused on just asking what is habitability. And we really emphasize in the discussion of how Europa Clipper will assess habitability that it's not just a binary. It's not saying, well, life could be here or life couldn't be there. It's also how long might life have been there, what kinds of life might have been there or might be able to be supported there. So that involves thinking about the environmental conditions, again, the chemistry, and also how the chemistry might have changed through time, how that chemistry equates to energetics and also materials available for life. Yeah, this is a figure, this is a graphic, it's kind of an infographic kind of thing. It's like a standard shape in PowerPoint, right? This like triangle of habitability, or the Triforce of habitability if you're a video game fan. So again, composition, energy, and water, these are kind of the guiding themes which we keep coming back to in our mission description. And that is infused in how we organized the structure of the mission, how we got to this point of thinking about ice shell composition, geology, and activity. It really started with chemistry, energy, and water, and really it comes to integrating across all of these different parts of Europa. This is an earlier figure, but it gets to the same idea, and it emphasizes the role of radiation in Europa in terms of this is a unique thing about Europa among other ocean worlds, is that same intense radiation environment that we're trying to minimize exposure to breaks apart water at the surface. Now, water is hydrogen and oxygen. Hydrogen is much less massive than water, and so will tend to escape than oxygen rather. And will tend to escape preferentially. So we can expect that the surface of Europa is oxygenated, and that means we have a possibility over geologic timescales to oxygenate Europa's ocean. And very optimistic estimates of this process lead to the conclusion that Europa's ocean could be oxygen-rich in a way similar to ours, and such that so that oxygenation was a necessity on life for the development of multicellular life. So it's the one place I can think of where we can actually imagine multicellular life. Now, whether that actually happened would be kind of jumping ahead to assume. And so typically we say, oh, we're mostly interested in looking for clues to single-cell microbes, but really we don't know. So getting into detail about these goals, the ice shell and ocean. This is getting into mission traceability, which is a standard thing in mission development, where you think about the overall goals and what you need to do to address them. So when we say ice shell and ocean, we really want to understand subsurface water, heterogeneity, and exchange across the different interfaces. And when we talk about composition, we're talking about the surface. We're talking about regional exchanges between those, and again, understanding exogenous versus endogenous things, and how all of that relates to the composition of the ocean. And I mentioned geology being a complex thing in Europa. We have to understand, how features on the surface formed, and where any recent activity might be. You can imagine those sites of recent activity are the place where you want to land in the future, and that's really what's driving that reconnaissance goal. We want to set the stage for a possible follow-on if Europa turns out to indeed be a really great place to look for life. Fish even, who knows? Okay, so, and I mentioned activity. It's not just plumes, it's also possible thermal anomalies, just indications that there is geological activity in the near history. Okay, so I want to emphasize this point about habitability by sharing a figure that was copied in the paper that I think is really entertaining. It's just displaying this is just summarizing all life on Earth in one figure. So you have pH on the x-axis, and this is really helpful for me as someone who didn't grow up doing chemistry. It breaks down pH into familiar terms. So on high pH, basic household bleach or ammonia. Low pH, battery acid. In between things like bananas, milk, egg whites. Okay. And so we can see then along that x-axis in the figure what kinds of organisms thrive in those conditions. And on the y-axis, we have temperature, going from the lowest extremes of a freezer, or the Himalayan midge, and going up to the extreme close to the boiling point of water, where there are some microbes that seem to be able to make a living incredibly. And so to investigate the conditions that might exist on Europa, including the entire range of conditions, if we think about whether volcanism might be there, and also acknowledge that the surface of Europa is about 110 Kelvin on average. We want to find how these conditions might or might not exist on Europa. So this is the instrument suite. This is the integrated investigation that I mentioned. For each of these the flybys that I showed you, there are 49 of them planned. All of these instruments will be on during the entirety of the flyby. And so we have a very capable, unprecedentedly capable suite of imaging instruments out in the UV. But there's some precedent. This one's on Juno. It's also on JUICE. So there's also somehow there's unprecedented sensitivity, but also heritage. So we go from the UV out to the thermal. These are all contributed instruments. This is a flagship mission, so these were competed instruments that were proposed by different institutions. And beyond that, in the radio, we have the radar that I mentioned before. We have two very capable imaging cameras in the visible range that are part of the imaging suite. ICE is those two cameras, so really this is two instruments. And then an infrared spectrometer that can see out to 5 microns to map compositional absorption features. So we're thinking hydrated salts in the 2.5 micron range and organic materials and volatiles out toward 5 microns. As a complement to those, for each flyby, we will sample materials in the in-situ space environment around Europa using 2 mass spectrometers, which have heritage from the Cassini mission, a neutral gas mass spectrometer that has unprecedented sensitivity, 10,000 mass resolution, if that means something to you. Happy to explain later. And measuring molecules up to 500 AMU. So we can actually look for peptides and things if those are lofted from Europa's surface. And some of the materials lofted from Europa's surface will be actual particles that are sputtered into space by radiation and also by micrometeorite impacts. And so the SUDA is the dust analyzer on Europa Clipper. Both of these are much more sensitive than the corresponding instruments that were on the Cassini mission that flew through the plumes of Enceladus. So along with the mass spectrometers, we also have a magnetospheric suite, namely a magnetometer suite and a plasma instrument suite, or PIMS, which are Faraday cups. It's a very cute name. And along with that, a gravity science experiment. So between measuring the magnetic field of Europa and the gravity field of Europa, we have a good chance of understanding the interior structure, especially when combined with radar sounding that hopefully will characterize the ice in great detail. So another view of the instruments. I don't know why that's there. Apologies. That's why, because they get organized in a really interesting way. So we can think about the theming of the mission in these themes that I mentioned to you before. So each of the instruments has a particular contribution to meeting the mission goals. This is where the integrated part comes in. I mentioned, the infrared spectrometer is thought of as mainly a compositional instrument, similarly the mass spectrometers. But they're also key to doing geology, right? The infrared imaging instrument has pretty good spatial resolution, and we can correlate its measurements with the visible imaging measurements because all of the measurements will be made at the same time. And so we can overlay those maps to understand Europa's geology and its composition at the same time. Similarly, the radar and thermal instrument are key to understanding the workings of the ice, and that understanding then contributes to our understanding of the deeper interior through the magnetic and gravity sounding. So, fundamental data, acquiring those masses and molecular masses, the IR and UV data, global mapping, so these are all the fundamentals that we're getting, radar reflections. These are all the different types of things that we're measuring directly, but these intrinsically are not habitability. Instead, we have to use models and analysis to interpret what these things are telling us, and we can then back out things like compositions, impact cratering distributions that have to do with the age of the surface. and ultimately get things like ice thickness and density structure, the transport processes. These things are still also not habitability. The things that we extract from them are habitability, namely salinities, water activity, which is sort of a measure of the ability of certain reactions to take place. Oxidation states, again, the availability of oxygen or hydrogen for reactions. These are the things that we will infer from that process of taking the measurements all together and comparing them with models and then understanding things about Europa that tell us about the habitability, hopefully the habitability through time. Okay, so having said all that then, here's the vision of a single flyby of Europa. This is a slightly older vision of the spacecraft, and this is developed in Cosmographia, which you can download yourself. And so you can see which instruments are on at any given time. Those are highlighted, and so right now the magnetometer and the PIMS instrument are on. You see Jupiter over there in the distance and Europa on the right. And you can see the time and the distance from Jupiter up in the upper right. This was an earlier vision of the mission, and so the date is more optimistic than what we're currently at. But the good news is that we did launch, so now we have a confirmed arrival time. So now you can see as we're getting closer to Europa, and the distance from Europa is in the upper left there, you can see that we're getting whole disk measurements of Europa, namely with e-Themis, and then a little band of measurement with the UV instrument. And as we're getting really close to Europa now below, as we come to around 10,000 kilometers, we'll start to turn on all of the instruments, and you'll see below 1,000 kilometers we're going to get the detailed suite of data. And you can see the orbital path in the lower right, the overall trajectory. So here it is. This is the flyby. Sped up. Yeah, exactly. Ah! And we did the same thing as we're going away from Europa. And so this will build up more than a gigabyte of data. And so one of the cost savings and technical savings of this design is that we can then take our time radioing back that information rather than having to integrate radiation-hardened solid-state drives onto the spacecraft and radio all that data back as we're obtaining it. So we spend 2 weeks, actually 3 weeks, radioing back those data on the, and here we're doing some occultations and other things, just as we were on the approach. So we spent the remaining time, the intervening time between this flyby and the next one, radioing back the data. You can imagine there might be some preliminary headlines before we do it all over again 3 weeks later. We do that 49 times. So it'll be a lot of fun, starting in 2031. This is a very NASA-y kind of figure. This is an Excel spreadsheet, so we do a lot of science in Excel. But this is really important. This is the mapping of the level 1 requirements. These are the high-level requirements that map to measurements and then instrument capabilities. So this is basically a restating of what I was telling you earlier about the, for example, how the ice shell and ocean measurements are done. This is expressing in detail what we want to do, right? So here, map the vertical surface structure where surface ice and ocean exchange might have happened at 3 kilometers depth. That then maps to measurements by ice, the visual cameras, and reason. So for each of these level 1 requirements, we can specify the science themes, so the full depth of the ocean, the shallow structure, and which of the instruments map to those. So this is an exercise in both understanding that if we lose one instrument because of that radiation, we'll still have the ability to recover some of that information. It's also emphasizing the complementarity and the synergy between the different measurements. So in that multiple layered Venn diagram that I showed you before is really trying to get at how we do this in a conceptual way. We expressed it in a kind of more crude way in the paper with this figure. This is the same information that I showed you in the Venn diagram. We also expressed that idea in a box model. This is kind of trying to get to the same ideas that are developed in Earth system science, where we can think about exchanges between different reservoirs, namely the ice shell, the ocean, and the mantle, and all the different processes that facilitate those exchanges. So on the surface of Europa, we have dilational bands. We have possible subduction. It's referred to as subsumption because the plate, you can imagine an ice plate getting absorbed into the warmer ice as it subducts, but then becomes warm and sort of integrated and no longer sinks. You can think of impacts and whether melting makes its way into the ocean. That's kind of a one-way process. Similarly, you have surface processes that that facilitate compositional changes on the surface. These are things that we could imagine ascribing quantities to and creating some kind of interacting system. So we go into that in some detail in the paper. I won't belabor these kind of walls of text. This is a more JPL-y kind of things. But suffice to say, there's a whole section on how Europa's formation and evolution determine the distribution of elements and energy. Similarly, we have a section on energy and tidal heating. I'll just back up a little bit to explain that the innermost 3 large moons of Jupiter are in a tidal resonance, an orbital resonance. So for every one orbit of Europa, Io orbits twice, and similarly for every one orbit of Ganymede, Europa orbits twice. And so that dance facilitates a forced eccentricity of those moons, and that the eccentricity, the non-circular nature of their orbits, means that as they're moving farther away and coming closer to Jupiter, they're flexing, and it's that flexing that creates the heat, that creates the volcanism on Io, and the possible volcanism on Europa. We have pretty good evidence for an ocean in Europa, though, and I'll explain why that is in the next little bit here as I move to the last part of the talk. But we were excited when we put this together that there was this recent result that if you model Europa in 3D, you arrive at a different answer than what was the commonly held wisdom at the time, but before that, for the preceding 20 years. And that is that you do possibly get volcanism in Europa's near mantle. That remains to be confirmed. So we also talk in the paper about the requirements for life. I mentioned hydrogen and nitrogen. These are the 6 main elements that life uses. Here we're calling it sponge. One of my colleagues really likes calling it that. Chinops is another way it's referred to. And in the paper we describe how the different instruments get at those measurements, really trying to drive home the complementarity of the investigations and the measurements. We have a section on drivers for energetic disequilibria. This is, in general terms, the kind of thing you want to think about. What are the redox fluxes? Where are the reservoirs for hydrogen and oxygen? Can we quantify those in a similar way to how this has been quantified for Earth? This is a figure from an earlier paper of mine on the x-axis, on the y-axis rather, showing the redox flux in moles per year of hydrogen and oxygen. This is something people do for Earth, right? So the battery terminals basically for life on Earth, photosynthesis generates net oxygen with roughly 10 to the 13th moles per year by the references that I was able to consult on that. And inventories of hydrogen from deep mines on Earth get you at about 10 to the 12th moles of hydrogen, or H2 per year. And so we did similar estimates for Europa, and depending on that big unknown factor about the oxygen generation and transport to the ocean, you might have those kinds of terminals offset by an order of magnitude or so for Europa, which is interesting when you think about Europa's smaller size. The per unit area fluxes are actually complementary for Europa. So again, reason for optimism. Maybe fish, who knows? I won't belabor this, but you can also go through, for those different oxidation states and molecules, what are the corresponding metabolic pathways that can support life. This is kind of old hat. This is from 1999, at the time when good evidence for an ocean was being revealed for Europa from the magnetic induction investigation that Galileo undertook. That still is the best evidence for an ocean in Europa. That is, that Europa responded to Jupiter's changing magnetic field by generating a field of its own. So I'll spend the remainder of my talk on that topic, which is the motivation for Europa Clipper's level 1 requirement to constrain the salinity of the ocean. Now, when we started formulating the mission, salinity was really equivalent to conductivity. The electrical conductivity of the ocean is proportional to the amount of ions in the ocean. But really, you don't want to know the amount of ions in the ocean. You want to know what ions are in the ocean. You want to know if you are in a reduced ocean state, more hydrogen-rich ocean. Perhaps that was Europa's early formation state. So this is a figure from my colleague Misha Zolotov showing the speciation of different ions. So you can think of sodium and chlorine, potassium, calcium. These are from chemical models, prudent models of Europa's likely bulk composition, then reacting those with the likely amounts of water in Europa, and coming up with the equilibrium abundances of different ions. If you put a lot of oxygen into Europa's ocean, as I was describing earlier, you might drive the hydrogen fugacity down. You might lower the pH to a more acidic state. and undergo this transition where magnesium and sulfate become much more soluble. So you can think of those as end members for a more hydrogen-rich or oxygen-rich ocean, which we know different types of life would prefer to be in. So my colleague Mohit Melwani Daswani, when he was working as a postdoc with me, did something similar and was able to look at how those ions also change with depth under the pressures in Europa's ocean. And that's something we can do increasingly. And so my interest in that time in working with Mohit on this paper and then trying to think about geophysical consequences was to ask, well, okay, I can actually simulate what is the depth dependent, what's the pressure temperature profile in Europa's ocean for a given ocean composition. Here, looking at seawater as a proxy for that reduced sodium chloride ocean or magnesium sulfate, and for different possible ice shell thicknesses, here 5 or 30 kilometers, also end members for Europa's ice. And the result is you have vastly different temperatures in the ocean, which then create different electrical conductivities. So then that becomes a question of if we can measure the magnetic response of Europa to Jupiter's field, can we tease out which of these compositions is more likely? And so that's what the journey we've embarked on in the last 5 years or so. So you can ask, what is magnetic sounding? What does that mean? Well, it's determining the physical properties at depth using magnetic measurements. That's kind of a simple way of saying it. It requires that we forward model Europa, as I was just showing you, using the best available data to predict the induced field, which we can do using the physics of how induction works. And then we have to compare those models with spacecraft data to infer what is statistically the most likely result. So to forward model the magnetic induction, you have to understand what that is. So Jupiter applies a field to Europa. As that field changes, as the changing field propagates through Europa, Europa induces a response that's opposite, that opposes the induced field. And if the conductivity of Europa's interior is not perfect, there's also a phase lag. So it's called a complex response. It has both an amplitude and a phase. And you can think of this in a graphical sense by visualizing Jupiter's field, this immense, powerful field, just the dipole component of the field. It's tilted and rotates at about 10 hours period, shorter than Earth's day. And so Europa sees a changing direction of field and creates its own field, as you can see there, as Europa orbits Jupiter. And so we can do some simple math, solve this problem of the diffusion of magnetic fields through Europa for a radial profile of Europa, and then we can simulate what Europa's ocean, how it responds to Jupiter's field. And so we do that with software that we've developed. We're increasingly trying to follow the lead of NASA's open source science initiative, the transformation to open science, this TOPS thing shown down here. And so I have this code called Planet Profile that creates these interior structure models. It relies intrinsically on the CFreeze code that Baptiste has developed and maintains, that it incorporates increasingly precise and powerful equations of state. And in recent years, we've applied this to multiple moons. So now, when you download Planet Profile from GitHub, you can immediately generate all these beautiful wedges of different moons that likely have oceans. And for different assumptions of the interior composition of an ocean and thickness of the ice, you can generate, for example, for Ganymede, where high-pressure ices exist and what the relative thicknesses of those layers are. So all of this is part of a project that's funded under NASA's Precursor Science Investigations for Europa, in which we're trying to do, speaking of multidimensional Venn diagrams, taking experiments and models and integrating them with data science methods to ultimately try to simulate the overall Europa Clipper investigation to back out the ocean salinity. So that involves intrinsically thermodynamic data on properties of the ocean, like the phase, the density rho, the thermal expansivity alpha. These are all things that go into the calculation of the interior structures. And so then the outputs are depth-dependent profiles of electrical conductivity, sigma, density, rho, which we can use to simulate the gravitational response, the tidal response of Europa. So we're putting all those together. We're working out the code to use the planet profile outputs to then model the response of Europa to Jupiter's magnetic field. And so my colleague Corey Cochran has this statistical approach, and I worked on this during the pandemic. This was my sit-at-home activity, figuring out how to construct tens of thousands of Europa models. And so this is kind of an abstraction of the output, but suffice to say, each of these is a model. Here we were actually doing this for Triton because we were trying to win a mission to Neptune's moon Triton, but same idea. So thousands of models of the moon with different properties of the ocean, and then asking whether the charged ionosphere on top of the body can explain a simulated induction response, a simulated imposed magnetic field and the corresponding induction response. And so for the simulated flyby of Neptune, the statistical approach matched the simulated data and found the most likely answer was here. You can imagine having actual data for Europa and having a suite of Europa simulations that span the phase space that we define, that is a very complex phase space of different ocean compositions and ice thicknesses, and the corresponding geophysical properties of the interior, and then backing out the properties of Europa's interior. And similarly, I mentioned we get density as a property, and we assume the ice thickness. We can simulate what is the gravitational response. Didn't get into this in great detail, but suffice to say, from the radio science experiment, we can measure the tidal potential of Europa, what's referred to as the love number K2, and from that we can back out what is the most likely ice thickness from the gravity constraints. So this is some work that my colleague Flavio Patricia did as part of his PhD. He's now working with us as a postdoc at JPL, just showing in this paper that you can get a statistical ranking of the ice thickness, but really it's correlated with the ocean thickness, right? It's degenerate, you would say. But if you then compare that with the simultaneous analysis of the magnetic field, you can narrow down the range, and this starts to look more like a Gaussian solution. So you would say, well, the most likely answer is an ocean thickness of 125 kilometers and an ice shell thickness of 20 kilometers in this simulated approach. That's the direction that we're headed. And I can mention that I've on one hand showed you these end members of magnesium sulfate rich and sodium chloride rich oceans, right? But really, we would like to be able to have our models speak to the full complexity of the ocean and its geophysical response. And so this year we made a lot of progress on that topic. If you're going to AGU, find me there. I'll have a poster. And we had an intern, Scott Cheng, who over the summer added this capability into Planet Profile that allows us to use this Reactoro code to take those simulated oceans that I showed you, with either different Zolotov simulations, different assumptions about Europa's ocean, or, for example, a seawater ocean. So this is just for one ice thickness. You can see how the different density profiles break out. This is density as a function of pressure. Here are the different temperature profiles. We also output sound speeds because we also want to do seismology for a future lander. And here are the electrical conductivities. And in the poster, we'll also show the magnetic and tidal responses as well. So this is getting toward the idea of having complex geochemical models for Europa and trying to figure out how we can match those to geophysical data. I could go into laboratory measurements that we're undertaking, but I feel like I've talked about a lot of different topics. So instead, I will jump to the conclusions, and thank you for your time. Time to wake up.
Any questions in the room?
Thank you. What would be the most, from your perspective, surprising but plausible result to come back from the Europa Clipper mission?
It's a narrow path. I would be surprised if the oxygen fluxes are as high as we thought. I would be surprised if the ice is at the lower limit of thickness. The lower bound on the ice thickness of Europa is 3 kilometers, which is constrained by the few craters on Europa that have a central peak feature, which requires 3 kilometers of thickness to sustain that peak. It's possible that that's the case. So that is the optimistic case for Europa that would be more consistent with fish. I'd be pleasantly surprised if that were the case, but it's plausible.
Thank you for a great talk. Cool. I was wondering how much, if any, coordination is happening with JUICE?
That is a great question. Yeah, so there's a working group that.
Can you remind what JUICE is?
Sorry. So people are also drinking orange juice in the morning. They're coordinating that, I hope. But no. So ESA, as a spinoff from the joint Jupiter SDT that Baptiste mentioned at the very beginning, we were working together during that science definition team period to have a Europa orbiter and a Ganymede orbiter. That was the dream, and we were going to work together as ESA and NASA and have this unprecedented collaboration, which was going to bring world peace and be the greatest thing ever. Instead, we couldn't keep it together, and now we have separate missions. But the good news is that NASA eventually committed to Europa Clipper. Shortly after the dissolution of the joint Jupiter Science Definition team, ESA went off and committed to a Ganymede orbiter, which is called the Jupiter Icy Moons Explorer, which somehow equates to an acronym JUICE. And so that mission already launched last year and will arrive slowly at Jupiter after 2031, after Europa Clipper. And so there's a team comprising scientists from Europa Clipper and scientists from JUICE, and they're working on how we can coordinate the measurements and make sure that we're sharing data as appropriate in a timely way. It's been noted by that study team, for example, that one of the flybys of Europa that Europa Clipper undertakes is followed or preceded by a JUICE flyby that's only 4 hours different and flies over the same territory in Europa. Now, they have very similar instruments, but they're not the same instruments. And so we'll be able to do really complementary measurements. In that context, I'll mention I'm sitting in the Outer Planets Assessment Group meeting this week while I'm here, and we had an update from JUICE today, and this is the result of the RIME radar measurements that they made at Earth's moon. That is our moon. You can tell I think about a lot of moons. Hey, we have a moon. It's amazing. And so we flew by the moon, and during this flyby, they were able to confirm that the radar that they carry, which is from the same team that developed the Reason radar for Europa Clipper, so RIME and Reason, they were able to. They can see the structure. Yeah, they did that. You can see the structure of the moon from the radar results. Yep.
Most NASA missions seem to go well beyond their planned life. What would you do with Europa after the, I guess it was planned 49 flybys?
Yeah, so before this year, the realization was that we would have plenty of fuel, and we were conservatively planning the mission based on our understanding of the function of the hardware, such that we could do the whole mission again. Since then, as has been covered in the New York Times and elsewhere, we've discovered that many of the MOSFETs, the 800 MOSFETs on the spacecraft, are not as resilient to radiation as the same MOSFETs from the same provider that were provided for the Juno mission. And so there was an intensive activity over the summer to study the consequences of that. So what it comes down to is these transistors will have defects in them that are supposed to anneal. That is, you can imagine the crystal sort of the semiconductor materials returning to their normal configuration through Brownian motion, sort of. So that annealing is prevented because of the manufacturing, the change in the manufacturing procedure for those MOSFETs. There were some mitigations, and so we think it will not impact the prime mission. Whether we do an extended mission is not clear, but the answer is that we would probably do more of the same. I can mention that in the spirit of the coordination as well, as part of getting into the orbit to tour Europa, we will have some incidental flybys of Callisto and Ganymede. And so there might be opportunities for coordination there before we do our prime mission. I wish I could be more optimistic about the extended mission. Yeah.
Yeah, I'm just going to add that maybe it's not confirmed yet, but Europa Clipper is supposed to fly. So the JUICE is supposed to capture an image of Europa Clipper crashing on Ganymede eventually. It's not confirmed yet, but that was in the idea, right?
Yeah, so there's a possibility that one or the other mission would see the other crashing into Ganymede, and that would be an opportunity for science unto itself. Yep. Yep.
Thanks so much. That was fascinating. I'm just kind of curious what you see as the possible pathways to or obstacles to an eventual lander. Like, in my mind, perhaps one of the most likely outcomes is we get fascinating data on the ocean and the ice shell. Maybe not much compositional information if there aren't plumes, and so we might really want to go to the surface to see what we're looking at and what are the
So this is a great chance to mention that before the pandemic and through the first year of the pandemic, there was a detailed study of a Europa lander, and during that last part of the 2010s, there was significant funding from Congress, namely from a congressman named John Culberson, who wrote into the appropriations budget that NASA would pursue a Europa lander. So there was a time when people were envisioning landing and flying by Europa at the same time. And that mission did a whole lot to robustly describe a mission that does multiple measurements to look for life. So the idea of looking for multiple overlapping biosignatures to really nail that down. And at least the study team was confident that even based on our current knowledge of Europa, we could find a compelling site and look for life. And so I hope that the result of the Europa Clipper mission is we will be even more confident of that. So maybe a next step is to land. Since that time, since Europa lander sort of stood down, there's been a lot of interest in demonstrating that we could drill through the ice. So we could land and just drill through the ice. I think the current wisdom on that is that you would need a compact nuclear fission device, which NASA is interested in building. It's a little bit not available currently. But there are people in this room who are thinking about these things in more detail than I am. Yeah.
Thanks.
You talked about potentially doing other flybys of the other moons of Jupiter. What information do you think we could get from that?
I'm really excited about doing flybys of Callisto and Ganymede. I think JUICE is going to knock it out of the park for the geophysical things that I'm excited about, but having complementary measurements from Europa Clipper will be great. So just emphasizing, we think Callisto has an ocean. It also had a magnetic induction response observed by Galileo, but a question at Callisto is, as for Triton, is can that instead be explained by charges above the surface? We don't know how thick the ice is on Callisto or how solid-state convection works there. Ganymede has an intrinsic magnetic field. It's the biggest moon in our solar system. It's the size of the planet Mercury. And it almost certainly has these exotic high-pressure ice phases at the bottom of its ocean. And its ocean is probably 800 kilometers thick. So it's a significant geophysical layer. A significant portion of the radius of Ganymede is just water. Again, JUICE will orbit Ganymede and address some of those questions, but Europa Clipper has something to contribute there as well. Yeah.
Any other questions?
I have a fun question for you. Other than the surface plumes, what is your favorite surface feature on Europa and why?
So the plumes are neat. I don't think I have a picture of chaos at Europa, but there are places at Europa where the surface is entirely destabilized. There are chaotic features on Mars as well. And so the idea is you have a solid surface that has, on a very short time scale, broken up, become jumbled and moved around. And Galileo provided images of a couple of these where you can see intact parts of a fracture system, and you can actually take apart the image and put it back together and see where things are. So the places where the ice has moved entirely are what are most fascinating to me, not least because you can imagine ways in which they mobilized materials that made their way into the ocean. So we've worked a little bit on the Darcy flow, the porous media flow, and whether brines under the ice would enable those things to move. So it's something we're thinking about in some detail. But don't make me pick a favorite.
Yeah, thank you. That was a really fantastic talk. I had a question about the Lucy spacecraft, as I know that's going to observe and measure Trojan asteroids, and I'm wondering if there will perhaps be some overlap in the composition of Trojans and some of the surface composition of Europa. What would you think what if there would be any overlap between those two?
Yeah,
missions?
you might know more about Lucy than I do, which is embarrassing to me. But I don't know everything. So Lucy will visit Trojans of Jupiter, and Trojans, kind of true to their name, are small bodies, asteroids that are stuck in Lagrange points. So these are stable gravitational points of Jupiter, like preceding and following its orbit, for example. And they might be clues to the materials that made Jupiter. And so in that way, Lucy might provide some information that we need to understand what actually is inside of Europa in the bulk elemental sense. Similarly, at OPAG today, the deputy project scientist for Europa Clipper, one of her roles on the project is to bring together observational astronomers to look at potential targets. This is not what I wanted to show you. No, I don't know if I actually have her slide. I do not, but I have other stuff from OPAG if you want me to show you later. State of the spacecraft, just since you're all looking at it. This is the update. Europa Clipper is alive, doing great. Nothing has gone wrong. Many things have been deployed. All the concerning things have been deployed. That's really exciting. But it's possible that astronomers on Earth will identify small targets, asteroids in the vicinity of Jupiter, and there will be opportunities to use Europa Clipper to look at small bodies in that environment. So that's one place where Lucy and Clipper might interact.
Okay, any other questions? Do you want to share some of the updates?
Just really quickly. So speaking of the launch, we launched on October 14th. That was really great. We were supposed to launch on October 10th. I was all set to fly out there the Sunday before. It was a Thursday. We were supposed to launch at 12:31. On the Saturday, the day before I was supposed to fly out, a anomaly developed in the Gulf of Mexico that turned into a Category 4. It was ultimately a Category 3 hurricane when it hit land. But I was one of the people who canceled their flights and ended up flying to Florida on that Friday. This hurricane touched down, its eye was over Kennedy Space Center at 12:31 on the 10th when we were supposed to launch. And so it was a pretty harrowing time for the people who were ensconced at the Cape taking care of the spacecraft. The science team was in a hotel that got clipped by a tornado. And I was sitting in my office at JPL watching the Florida news and hoping they were okay. It was an eventful year between the MOSFETs and the hurricane, but we're in pretty good shape now.
Well, thank you, Steve.
Yeah, all right.
Thanks.
And I'm around if people want to chat.
Yeah, we're going to stay around for another hour, 45 minutes, so if you want to come chat with Steve, please do.
Yep. So, yeah, and you were here for this. You were there for this part? This is data from the magnetometer.
No, I wasn't there.
Yeah, so this is the data for the deployment of the magnetometer. And so they were able to see, this spiral shows the unfurling. Yeah. And then...
that's really cool.
Yeah, and there's the reason they were able to see the electromagnetic interference of the spacecraft as they were deploying. Yeah, thanks for coming. So.
That's really cool.
Yeah.
Okay, do you want to unlock your thing?
Sure.
Yes, what are you doing?